does everybody have something written down? Okay. So I'm going to tell you why we're doing this, and it's mainly because I was hired under a soil health initiative, and I struggled to figure out what soil health means to the state of North Dakota. I mean, you can find definitions of it all over the internet. You can look at soil quality, you can look at soil health, and the transition from soil quality into soil health, and how the definition is constantly changing. But what I want to know, and what we want to know from the Soil Health Initiative group of hires, is what does it mean for North Dakota, and where should we be taking our efforts as far as soil health is to best serve the state. So I appreciate you guys filling those out. And does anyone want to share any of their ideas on what soil health is? I see some people shaking their heads no. Absolutely not. Okay, well, I'll tell you what it means to me. And this has been, I say, a working definition because it's constantly changing for me. Every time I speak with somebody different across the state, or I learn something new, I slightly tweak my definition of soil health. And so for me right now, it means selection of management practices to achieve desirable, site-specific soil conditions that meet on-farm goals and contribute to environmental services. So maybe in a year this definition will be like a paragraph long because I keep adding to it, but for me the important parts are management practices. Soil health is something that we're managing, that we're actively managing. It's the dynamic quality of the soil. Site-specific soil conditions. I don't think every site is created equal. Not every soil can achieve the same level of soil health. So we're talking site-specific. On-farm goals. I think that some aspect of soil health has to fit in with the producer's yield goals or their business plan, whatever they're trying to get out of the soil. And then environmental services, because we know that soil health is extremely important for the environment, for sustainability, and those kinds of things. So that's where my definition comes from. Does anybody have a similar kind of definition to that? Sometimes I get just profit. I mean, and that makes sense. You know, maybe you're building soil health to have a profit, and that's fine. That's good as long as we're aware of what soil health is, because it is a touchy-feely term, and it's something that maybe most of us don't sit down and actually think about what it is. But today what I'm going to do is talk about it in the terms of aggregation, soil biology, and organic matter. And so those are three terms that you hear pretty often when you hear soil health, right? I mean, everybody says build aggregates, feed your soil biology, build organic matter, watch the percentage of organic matter increase. And you know, what do all those things actually mean in the context of science? What is an aggregate? What is soil biology? So we're going to go back to the basics. We'll cover what those things are, what they do in the system, and then how does management affect aggregation. And I don't know if Mitch and Annie Hohenhaus are here yet, but I have some, we went out and sampled some of their sites where they're no-till farmers in Lisbon, and so what we did is we went out and sampled some soils from there, and I have some different systems where we've collected samples that reflect aggregation and soil biology, and then also organic matter. So we'll kind of do a little case study here. Okay, so this thing kind of zooms around a bit. So what is an aggregate? How many of you have really thought about it when you pick up a handful of soil, what an aggregate is? Lee has. Thank you. Chris has. Okay, we got some people responding. This is good. Well, an aggregate, there's a difference in my mind. I've worked with aggregates for 10 years, and you can probably imagine that would be pretty boring to look at aggregates for 10 years. But there's a huge difference between just a structural aggregate and a functional aggregate. I mean, when you start looking at these things pretty closely, there's a big difference. We do know that aggregates are built by organic additions from plant and plant roots. So when you have organic matter added to the soil, it serves as a nucleus for aggregate formation. And what I mean by that is there's organic matter, it's feeding microbes, it's feeding bacteria and things like that are chewing away on the organic matter. And when they're chewing away on it, they're secreting glues, which are actually gluing the soil particles together. And that's the foundation for an aggregate, a functional one. We know they come in various sizes. There are what's called macroaggregates and microaggregates. So when you pick up a handful of soil, you see larger aggregates, and then you see the smaller ones that kind of fall to the bottom. It's important to have different size aggregates in the system. You don't want all the same size aggregate, because we know that aggregates build pore space, right? So if you had all the same size aggregate, you're going to have all the same size pore space. And we want variable pore space, and we'll talk a little more about that. And we know that aggregates have different turnover times. So a larger aggregate turns over quicker than a smaller aggregate. So we're talking in terms of maybe 40 years for a large aggregate and hundreds of years for a small aggregate. Okay, so what's the difference in these two aggregates? Residue, exactly. So this one on the bottom, I don't see any roots or anything forming those aggregates. They're aggregates, and they're probably a structural aggregate. You can see one root right through here. But this aggregate, when you look at this, and this is from Mitch and Andy's place in Lisbon, you can see all kinds of roots wrapping around there. I think there's actually a small worm in that aggregate. You can see all the residue that's there. You can see that there's probably organic matter serving as kind of the nucleus for that aggregate to form, versus this one on the bottom that's more of a structural aggregate. So are we getting more in our system out of this aggregate versus that one? Yeah. And you're getting both the structure and the pore space built by this aggregate, but you're also getting this nutrient cycling component and habitat for microbial habitat. So they're very different. So here's a closer picture of it. And what I thought I would do, because I spent some time looking at YouTube videos, is this is actually an image of flying through an aggregate. So you can see, look at all this pore space that exists within that aggregate. I mean, this is all habitat for microbes to live in these little nooks and crannies within an aggregate. That's room for organic matter to be stashed away and stored. And as this aggregate turns over, that organic matter becomes available. So this is, I mean, pretty wild when you think of flying through a soil aggregate, but it shows the function that that aggregate would have in a soil system. Okay, so what does an aggregate do? Provides pore space. So we talked about the different size aggregates. If you have larger aggregates and smaller aggregates, you're going to have different size pore space. And what moves through pores? Air and water, right? So if you have larger pores, you're going to get quicker water flow through those pores. If you have smaller pores, it's going to hold the water a little bit tighter. You're going to have airflow to provide the oxygen for the soil microbes to function. So that's a really important part of aggregates. But they also regulate nutrient cycling because they're holding organic matter on the interior of them, right? And if they turn over and release that organic matter, that's a form of regulation of nutrient cycling. So that organic matter becomes available at different times based on that turnover of that aggregate. And erosion control, I think we talk a lot about raindrop splash, and having an aggregated soil actually reduces the impact from raindrops. But in North Dakota, we have a lot of wind erosion. So if you have soil particles all glued together in larger packets, you've got more of this kind of creep going on as opposed to the suspension of those particles in the air. So, so that's a really important function of aggregates. Okay, and how does management affect aggregation? Well, we'll go into Mitch and Andy's place. So we have the first site that was sampled is this pasture. In 2012, this pasture and went into no-till corn in 2013. So here's a picture of that. You can see all the residue on the surface. You can see the corn. And I can't remember, what were the yields they were expecting out there? Sorry.
It's like 150. You did a yield estimate.
Okay, yeah, 150. That's not bad, right? I mean, that's a good yield. So they're putting this right into pasture. I see Mitch and Andy are now here in the back. So this is the field we sampled for all of the PSCAM people in the room. This is from the web soil survey. Here are the sample locations. We targeted the beard soil, or barn soil, sorry. And we just went out, we pulled a couple samples from here, from the surface, and down from 6 to 12 inches, just to look at what it was. So, okay, so we've got a corn going into no-till corn going into pasture. The next site, it was CRP in 2007, no-till into corn in 2008. Beans, wheat, winter wheat cover crop, peas cover crop, corn cover crop. So you can see this cover crop is growing in here, and I think maybe they'll tell you how they got that in there later during their talk. But they've done some really great things out there. So this is a no-till corn cover crop system. And again, we're looking at the barn soil type we sampled in this area here to get the soils. And then we sampled a field that was not under their management because it's a conventional till site. Again, with a similar soil series on it, and that was in corn. So, if we look at the aggregates, the blue here, those are these large macro aggregates. So that's 2 millimeters to 8 millimeters in size. So they're large. They're the ones that picture was over. They have all the residue in there and all the organic material. And when you have large macro aggregates, that means you have minimal disturbance, basically. I mean, these aggregates are able to form. So in the pasture, in the corn system, we have 44% of that soil is actually in those large macro aggregates. And then the red are small macro aggregates, were almost the same thing, they're just a little bit smaller. So a good portion of that soil is held up in those aggregates. And that's really important, and that's something that, that is very difficult to achieve if you have a lot of disturbance in the system. When we look at the corn cover crop, so have a good percentage of blue and the red combined. Those are our macro aggregates. So that means that that system is very, it's intact, it's functioning. Those aggregates have fungal hyphae and roots wrapping around them. They're actually serving a purpose of protecting organic matter. But when you look at this conventional system, you have very few large macro aggregates, only 4%. And that's not a whole lot. I mean, those things can't hold up to all that tillage. And then when you look at small macro aggregates, and then this large portion of really small micro aggregates. And that is really indicative of a system with a lot of disturbance. So they've been able to build, if they're starting with this, they've been able to maintain most of that aggregate structure using corn and cover crops in diverse rotations and no-till. So that's an important thing to notice. Okay, does anybody have any questions on aggregates?
Where's your cutoff in size on the micro and the next level up?
The micro and the macro and the small macro? 250 micron.
What were the questions?
The size break between the micro aggregates and the small macro aggregates is 250 microns. So if you're looking at that mesh, it's just a really fine mesh. And those actually, with aggregates, you can get all different kinds of breakdowns on sizes, but this is just one school of thought on those. Any other questions on aggregates? Nope, everybody's going to look at it. Yep, in the back.
Could you repeat the questions when they're asked up front so we can catch it all down there?
Yep,
Thanks.
will do. Okay, so soil biology. What are we looking at with soil biology? Bacteria, actinomycetes, which are just a filamentous bacteria, and fungi. We also, in this group, we talk about earthworms and other macrofauna. We know earthworms are extremely important for building soil structure. They serve a huge function in the soil. You have earthworms, that generally indication of a very high functioning soil, a very healthy soil. But they do more than just create pore space. And I don't know if I can forward through this or not and get to the earthworm part. Okay. So when you search worms on YouTube, be prepared if you want to kind of throw up, because I have pictures of people eating worms and stuff too. But this is an earthworm going through the soil, and you can see all this black in here is actually soil that it's ingesting as it moves through. So worms do more than just move through and create this large pore space. They're actually ingesting soil, and when they do that, they actually create aggregates. And when they kick those out, they're forming structure in the soil. So that's another function of aggregates people don't think about, is that they're actually, have all the bacteria and stuff in their guts actually helps form aggregates because it glues them together and then they excrete them back into the soil. So what does soil biology do? Well, decomposition of organic matter, nutrient cycling. Microbes don't generally like to create nutrients for plants to take up, but they're kind of leaky and they don't do as good of a job as they could. So when they're not using all those inorganic forms like the nitrates for their own building of their cells, they actually leak them into the soil, and that becomes available for plants. Fixation of nitrogen through bacteria, nodulation on roots, and also the maintenance of soil aggregates. So you have bacteria on the interior of aggregates cycling organic matter and secreting glues, but you also have fungal hyphae wrapping around aggregates in the soil, creating those large macros and holding those particles together. So one of the things I love to talk about is one of the most famous aggregate scientists in the country. She talks about the importance of fungal hyphae in aggregates, and she says they form what's called a sticky string bag. And it doesn't sound very scientific, but it's very true, because you have all these fungal hyphae pieces wrapping around soil particles, and they secrete this glue and actually stick all those particles together and create large aggregates. So when you imagine if you have some kind of disturbance or tillage or something, and you're ripping apart these hyphae, you're actually destroying those aggregates. So how does management affect soil biology? Again, we're going back to Mitch and Andy's place. We'll look at microbial activity first. Here's the Sylvia test, which you'll hear plenty about later. But we have the three systems. Here's the no-till pasture corn, no-till corn cover crop, and then continuous or conventional till corn. And so you can see the color on these is, I guess, let me show you the scale of color 0 to 5. So obviously the lighter color means higher CO2. When we're saying CO2, we're looking at microbial respiration or activity. So we have a 3.87 for color on the pasture, 3.79 on the corn cover crops. So those are the same as far as microbial activity, but much lower in the conventional system. The microbes aren't as active in that conventional system as they are in the pasture, in the corn, or the corn with cover crop. So if we look at rootling, this is something we're starting to do more in my lab with looking at actually scanning the roots from a sample, from a volumetric sample collected from the soil. So when you look at all this root area that forms what's called the rhizosphere, that's the most active part of the soil where the microbes are doing the most work. Look at all these roots that are existing within that pasture, the residual roots from that system. And then even with corn and cover crop, you start seeing reduced roots. And maybe they're deeper or the structure's changed, but the thing to note is the change from this system to the corn with cover crop. I mean, it's tough to achieve those same levels of roots as you can with a pasture system versus a cropping system. Okay, does anybody have any questions about soil biology?
You hear a lot of negative talks about nematodes. Can you talk a little bit positive things about nematodes and how they help in the system?
Okay, so Fran was asking you about you hear a lot of negative things about nematodes because they're feeding on roots and things like that. But there are some positive things about nematodes, and they're part of the soil food web. I mean, they're part of what keep all those things in check. And somebody may have a better answer, maybe Jay or Fran, you probably have a better answer for that if you'd like to answer that question. But they can be beneficial because they can feed on each other and keep predatory nematodes in balance in the system. They can also, I don't know, what else do nematodes do?
I think even the ones that we call bad play a role, and we have to have them. And I think it's only when it's out of balance that we put that label on. We got to have a balance in there to make the nematode portion work. Because I think as far as mineralization, I think they actually have a larger impact than protozoa. What I've read.
Yes, I think that's an important, when Jay says in balance, I think that's really important. Have all these different microbial groups and macrofauna and microfauna in balance in the system, all functioning how they should be. Any more questions on soil biology?
I have a question for Abbey. We've taken the soil biology analysis for a number of years, and every now and then we run into fields with no protozoa. And then usually we'll go back later, resample it, just to kind of do a check. But many times that field just has no protozoa. Any thoughts on that? How does that occur, or how do we bring that back?
So Jay is talking about protozoa in the soil, and I am not a soil microbiologist, so I'll just tell you that right now. Anne Marie Fortuna is. I don't know how to bring them back or how to get this thing back in balance. So that's a good question. I don't know the answer. I'm not how to bring protozoa back. Does anybody else have an idea on how to do that? Okay. Maybe we'll talk about that more over lunch or something.
One thought we had is livestock.
Okay.
Play a role.
So Jay's saying maybe livestock would play a role in bringing back protozoa. In that. Okay. Let's talk a little bit about organic matter. This is another area I've worked in for about 10 years. What is organic matter? It's built by root turnover, root inputs, residue, additions of manures and compost. Something that's not thought of often with organic matter is that it's actually stabilized in 3 ways. It's called biochemical recalcitrance, and that basically means that microbes won't use it because it tastes bad. I mean, it's the chains that it has, the type of organic material it is, that they won't actually utilize it and it'll persist in the soil. Chemical stabilization is another way, and where organic matter is actually chemically attaching to silt and clay particles in the soil, so microbes can't pull that off. And then physical protection, here's the aggregate part. So you have organic matter on the interior of an aggregate, and the microbes just can't get to it because it's protected by all the soil particles around it. So that's something important to think about when you're talking about organic matter. It's not just like putting it into the soil, but it's figuring out how it's being stabilized in the soil so that it can persist. So we're talking about like chemical stabilization. That's mainly like your dark color in the soil that you get is primarily from this mechanism of protection. The aggregates obviously here, and then biochemical recalcitrants, that's some of the litter that you may just have in the soil that's just not being decomposed because microbes just won't go after that. So it's important to think about how these protection mechanisms are working within the soil. And then I also encourage people to think about, instead of looking at just your organic matter percent, I mean, I think that's one of the things we get our soil test back and we look at percent organic matter and we see is it increasing or decreasing, is to think about where that organic matter is and what pools it's in. So here's an example. This would be an available pool. It's like a 5-year turnover time. That's what's between soil aggregates in the soil. I floated off in a lab with a high density solution, so this is stuff that microbes are feeding on in the 1 to 5 year time frame. Then you have this whole group of aggregate protected organic matter, right? So that's more of like the 40-year time frame that's protected, and then the mineral bound, which is the stuff attached to silt and clay. So it's really important to look at how this organic matter is being incorporated into the soil, which groups it's actually going into, versus just looking at a total percentage of organic matter increase in the soil. So what does organic matter do? It's a nutrient source, helps retain nutrients because it has the charges on its surface that holds nutrients. The soil is cropped, the pool is decreasing as far as the available pool. When we look at the aggregate protected, we have about 15% here in this no-till pasture. There's an immense amount of organic material protected within aggregates in the system. And we have about 5% in a corn cover crop and 2.4% in a conventional till system. So there's a huge shift in how this organic matter is being protected in the soil. And if this is easier to look at visually, here's those two pools, the available and the aggregate protected in that pasture system versus the other two. And these are the numbers you get back in a soil test for percent organic matter. 9.2% total organic matter in that system, 5.8 to 4.4. So you may look at, a soil test and see 4.4 here, and maybe jump up to 5.8 going no-till or something like that. But it's important to know that where that organic matter is located. And here there's not a whole lot that's available in kind of the medium term as aggregates. So that's why I just encourage people to think about where the organic matter is held in the soil. So that's what I have for aggregation, soil biology, organic matter, and systems. So hopefully help define those terms a little better for people that are encouraged to build aggregates or to feed their soil biology or to build organic matter. Does anyone have any questions? I think we have about 5 minutes for questions. Yeah, John.
On the one side, you shows a rich length of different systems, and try to drop off between the pasture and the middle one with no-till corn, and the third one was conventional. Were you surprised by the drop off there? Almost the same length of conventional versus?
Yeah, I thought there'd be I'm always surprised in the lab. I never know what I'm going to find, and maybe it's because of where we sampled was kind of the interspace between the crops, so there wouldn't be as many roots, and the cover crop is relatively young. And we have some.
Well, I just had a comment on that. That's, it's first year out, and you think about the weed control that we did within year 1, year 2, we're really only growing a crop on about 17% of the soil when you look at a dirt control, really. And so you take a system like that that's actually pasture, which is inundated with every square inch trying to cover. I think there's an explanation just there on how much we're really growing. We're going to a monocrop, even though it's in a no-till system. I think that's really a huge jump. Because we were out there, it was soft, and I was commenting to them. I was like, "You guys did an excellent job of getting the seed in the ground." That was that kind of a challenge. So that's just a comment.
So did you find that a lot of people are accepting, especially the scientists in this area, soil health of using aggregates or exploring everything at the aggregate level? Because personally I found that a lot of people, even if they're working with soil food web, they ignore this concept of aggregates. Although we all know that different organic matter quality and quantities are stored in these aggregates with totally different microbial communities, performing different functions, yet people are neglecting that and just continuing averaging out like soil is a uniform kind of the media. So what is your, especially North Dakota, I mean, do you find any positive signs of people accepting it?
So the question was, are people accepting the idea of aggregation as being important in North Dakota soils? And I think there's an awareness that people know that aggregates are important. They may not know exactly why they need aggregates, but I think we're making big advances in that area. I mean, it's one of the easiest tests that can be done if you have, just 5 minutes to run the analysis. It's an easy test to run, and it's an easy one to interpret. So I think there's a lot of value in that. And then maybe that's one of the soil health parameters that we should be looking at, is the aggregate size distribution. Do we have a lot of large ones or a lot of small ones? If you have a lot of large ones, your system's generally healthy. If you have a lot of small ones, there's a lot of disturbance and it's relatively unhealthy. So, so I think it's a good parameter to look at, and obviously I'm partial to it because I've been working with them for so long.
As a producer, trying to do soil health, what are the means, I'm looking for measurements. What are the measurements that we are to look at to know that we are improving our soil health?
Okay, so the question was about measurements for a producer to look at actual improvements to soil health. I think if you were to look at something like aggregate size distribution, that would be important. Finding a place to do that, maybe we can talk John Lee into doing that in the future. But I think that's an important measure. I think the Solvita test is very useful because it's a color, so you can see very quickly what the microbial activity is, and it's easy. You just fill a jar and then you put a card in there and you look for a color change. Obviously that organic matter fractionation, that would be a tough thing for a guy to do, and that's an expensive analysis. But you could do it. You could basically take a soil and you dried it, and then you could use table salt and create a high density fluid, and then you could dump that into your soil and float off some material, and visually you could just see that there's a difference. But I think those parameters are important. I think we need to maybe get away from using fertility as a guide for our soil health, and start looking at these things that we're always talking about as important parameters for soil health we're trying to build. So I probably didn't give you a really clear answer on what you can test, but
No, but I guess I've always, the only thing that we have is the technical accuracy, but
yeah, and organic matter is a tough one to look at because when that's measured in the lab, and John and I were just talking about this the other day, it includes a lot of the litter and things that aren't actually part of that organic matter pool. So those numbers are pushed artificially high, and they're not going to be a good indication of what you have. And so any sample that you pull, you might have different amounts of litter in it. So if you pulled from 1 year and you didn't have a lot of litter, say you're pulling from a soybean or something, and then you pull from a corn, you have more litter or something, then you're seeing this boost. You're like, oh, I have all this organic matter, but it's an artificial. It's not really material that's in the soil. So we do need to have better measures for soil health.
Have you maybe used filtration tests? Have you used that much?
I haven't. I think we're going to start using it a little more. I know you guys use it a lot with NRCS, the infiltration test, and that's a good indicator too. Is how is water moving through your soil? How quickly is it moving through the soil?
Question, so you mentioned that protected organic matter fraction. Is that the part that's still in play?
So he's asking about the protected organic matter fraction. That was what was within aggregates. So you can see when you float off just that available pool, there's so much more that's actually protected within the aggregates that's a better measure of soil health in my mind.
How about the little bit there you said, the fraction that's within is still in play, correct? And is that the part that's going to be consistent year after year that you see maybe in the range settings?
Yeah, you would see very little change in that part that's attached to silt and clay. The only place I've ever seen a change in that fraction is in wineland, where you totally annihilate the soil and then put it back. And that's the only place I've ever seen where you lose organic matter from that pool and then start building it.
Abbey, from producer's perspective, I believe Dr. Haney's soil test, water extractable carbon and nitrogen are maybe something that we easily sample for.
So we'll cover different types of tests producers can use for organic matter and also soil biological activities, so that'll be perfect.
Remark,